Welcome to homework.
Often, it's a difficult challenge to try to determine the levels of energy within an atom or molecule by just studying the spectrum of radiation that comes out through transitions. As an example of this, suppose we had an atom with three unique energy levels. And let me exaggerate those so I can show the transitions. But the energy levels are all three unique. We'll call them E1 for the lowest one, E2 and E3. Let's just show the transitions that could occur. So we'll start with the top level. It could fall down one level. It could fall down two levels. Or it could fall down from the second level once it reached that point. But notice that all three energy differences are different. So these would produce three unique wavelengths of radiation. Now let's consider a situation in which there are three energy levels, but the spacing between the levels is identical. And this is, by the way, a harmonic oscillator type situation. So we have E1, E2, and E3. So our first drop, no problem there. Our second drop, that looks unique. But look at our third energy difference. Identical. So the red and the green, unless there's some other way to distinguish them, would have identical wavelengths. And that means you may only think there's less energy levels than there are if you had a system with this type of structure. So identical wavelengths. But this is why, the energy differences are the same. And this means only two unique wavelengths come out. But this is why spectroscopists often experiment with atoms by putting them in electric fields, in magnetic fields, looking at the polarization of the radiation that comes out. All these kinds of tricks allow them to separate out photons that may, by identical wavelengths, but can be changed or looked at in a different way to identify energy levels in the atom better.